Hey everyone. So, hey everyone. In this video, we're going to be mastering the softmax function or layer with a focus on neural networks, right? So the context is still the email classifier we're building as part of this series on neural networks for classification. Now, the softmax function is actually a very important or key function in neural networks. In our case, we're going to use it as the last layer to convert the outputs of the linear layers, or rather the tanh layers we have learned in the previous video, learned how to set up in the previous video, to convert that into the output that will help us predict, what class the email belongs to, and also use it to train the network. And softmax shows up in a lot of places. It's very key. So even something like large language models, the transformer involves the softmax function, right? So understanding this is going to be exceptionally important if you have a career in deep learning, right? Okay. So the softmax is basically a very simple function, right? It takes in an input z where you can think of z as a vector with n dimensions, so z1, z2, and so on. It takes that value in, and then what it does is each s of that softmax. So s, the output, is also going to be a vector of the same dimension, right, with the same number of values basically. And each SI or AI, whichever way you want to call it, which is the output, is go for each ZI is the exponential of ZI by the sum of the exponentials of Z, right? So you basically take the exponential of each of these terms, you sum it up, that's the denominator. And then for each ZI, the exponential of ZI is the numerator. So why is this so important? Well, first thing, as we can see, if there are three inputs, for example, there'll be three outputs, right? The softmax will give you the same number of outputs, right? And also, it has no parameter, right? As you can see, it's just an exponential function in the numerator and the sum of those exponentials in the denominator. So there are no parameters, right? Which means when you backpropagate, you're just going to pass the sensitivities through this. Meaning there are no, you're going to have to get the sensitivities that are passed back, but there's no parameter that you're getting the weights for. So let's look at an example. Let's say the neural network, is designed with three outputs at the end. So let's say it's minus 0.3, 0.2, and 0.7. We're going to call it Zi. First, we compute e to the power of Zi. So what do you get? E to the power of minus 0.3, which is 0.74, e to the power of 0.2, which is 1.22, and e to the power of 0.7, which is 2.01. Sum this up, you get 3.975. And so the softmax output will now be this divided by this divided by this, and this divided by this, which is this set of values. So what have we done actually? You just kind of observe this, fairly carefully. We've taken these values, and now if you see the sum of this, right, is equal to 1. So effectively, the output of the softmax can now be treated as a set of probabilities, right? It sums to 1. And so it breaks the output of whatever is passed in, typically the last hidden layer of the neural network, into probabilities. And now you can say, well, given this set of values, the probability is 51% that it's spam, 31% that it's marketing, and 18% that it's an important email, right? Given a particular email. We're not worried about what email is, just assume this vector represents what you get at the end of the last hidden layer. So when you're trained now that was the simple forward pass through the softmax. That's and it's a functional layer, so that's all it is. But now what's key also is how you train with softmax, right? So Z goes in, A comes out, and now you have a loss function because typically this is the last layer of the neural network. So all these A's, we're going to call the output of the softmax function A's, similar to what we have done in the previous layer, the output of a neuron or a layer, we're calling them A's, right? So the A's come out and get fed into the loss. The loss takes the actual label or the actual values, gives you a loss. And what it also does then is gives you a sensitivity, right? Which is going to be the sensitivity of the loss with respect to the values fed in, right? So the A1, the A2, and the A3, which are the outputs of the softmax. When you get these then are passed back into the softmax, right? And now, so backpropagation has started. Softmax is going to have its sensitivities, right? The sensitivities of the output of the softmax with respect to the input. We need to compute those. And then using chain rule, what we get is the sensitivity of the loss with respect to the inputs to the softmax, which is then passed further back. So like I said, there are no parameters in the softmax, so you don't have to worry about that. But these then have to be passed back through the network so that you get the sensitivities with respect to the weights and biases of all the other layers, right? In our case, they are tanh layers, right? So they do have weights and biases. So we need to, of the linear part of the tanh layers, right? Just to be clear. Okay. So, well, how do you get these sensitivities? Okay, so this is little math, but I'll try and go through it as cleanly as possible. So you have three inputs and three outputs. You need the sensitivity of each of these outputs with respect to each of these inputs. Till now, what we've seen is a tanh neuron. And so even the linear part has had just one output, right? And you have got the sensitivity output with respect to the parameters. In this case, you've got multiple outputs and multiple inputs. So what you end up with is a matrix, right? You end up with a matrix. And so the partial or the derivative of the output A, I, with respect to the input Zj is what we need, which is a matrix. So derivative of A1 with respect to Z1, derivative of A1 with respect to Z2, A1 with respect to Z3, A2 with respect to Z1, A2 with respect to Z2, A2 with respect to Z3. Then, of course, A3 with respect to Z1, A3 with respect to Z2, and A3 with respect to Z3. So I'm assuming in this case there are three inputs. If you have 10, you would have a matrix, 10 by 10 matrix, and you would have the sensitivities, right, of each of the outputs with respect to each of these inputs. When you look at this, and now I'm going to focus on a 3 by 3, just to keep it simple. So assume three outputs and three inputs. There are the terms on the diagonal of this matrix. So we're going to say the diagonal terms, which is basically for dou AI. So ith output versus the jth input. We're going to have the term where j is equal to I. First input versus first output, first input versus second input versus second output, and third input versus third output. And then we have the off diagonal term, right, which is the derivative of I with respect to j, AI with respect to zj, when j is not equal to I. I'm going to break this derivative into these two parts and compute them for these two separately because there's a slight difference in the values. How do we do that? Let's do some math, right? So the softmax function is this function. Let's take the derivative with respect to a zi. So we're saying j is equal to I. So we are basically just going to focus on the derivative of ai with respect to zi. So dou by dou zi of this term, right? And here again, I've said zi. So zi is the numerator. Now we know for the derivative of a fractional term, derivative of u by v is v du minus u dv by v square. So the denominator is v square. So sigma j equal to 1 to k e to the power of zj square. That shows up here. And then it's v du. So it's this denominator terms times the derivative of ei by zi minus u dv. So u is this. So e zi times the derivative of this, the sum term, right? Okay. Now, the derivative of zi with respect to zi, that is the derivative of e to the power of zi with respect to zi is e to the power of zi. So we can first make that change. And then what we're going to do is we're going to focus on this term, right? It's a slightly biggish term. Let's just differentiate this first. So the derivative of zi with respect to the sum of e to the power of zj. So dou by dou zi of e to the power of z1 plus e to the power of z2 and so on. Now the only dependence is on the corresponding zi, right? So it's dou e to the power of zi by dou zi. All the other terms go to 0. And that's e to the power of zi, right? So let's substitute this back, right? And what you end up with is this term now gets replaced by e to the power of zi. And so what you have now is this term, I'm just splitting it, right? And then this term, we've just separated the the numerator, the two terms. Why have we done that? Well, we can now rewrite this, right, as you can cancel here the numerator term, the summation term here, because the same thing appears in a square in the denominator. You can take out the square and cancel this from the top. You're left with e to the power of zi by j equal to 1 to k e to the power of zj minus e to the power of zi by this. I'm taking the square outside because this is e to the power of zi squared. And this is sigma j equal to 1 to k e to the power of zj. Why have we done this like this? Well, we know that the output AI is basically this term, right? So Now the derivative of AI with respect to Zi can be written in terms of AI, right? Which is what we always do with activation functions in neural networks. We always try to write them in terms of the output. So you've got AI minus AI square, which can also be written as AI into 1 minus AI. So the derivative of the diagonal term is this. What about the off diagonal terms, right? So j is not equal to I. So the derivative of AI with respect to Zj, in the other case, it was AI with respect to Zi, right? This is with respect to Zj. So you have e to the power of Zi by Zj, and we know j is not equal to I, right? So for that case, this term has gone to zero. There's no dependence on Zi with respect to Zj, right? Which means this whole left hand side is gone. This term here, the left of the subtraction has gone to zero. That leaves us with this term, right? Now we've already seen this term before. Let's just focus on that. Only difference is now it's with respect to Zj, where j is not equal to I, which doesn't matter. All the other terms, there's no dependence on. There's only dependence on one term, e to the power of Zj. So it's the derivative of e to the power of Zj with respect to Zj, which is e to the power of Zj, right? So we can substitute this back. In the previous case, it was Zi. In this case, it's Zj. So it's dou Ai by dou Zj is e to the power of Zi times e to the power of Zj by the denominator term. What are we going to do? We're going to break it into two parts again, but now this time it's a multiplication. We have the negative sign out. So e to the power of Zi by this denominator term, which is basically the softmax of Zi, e to the power of Zj with respect to by this denominator term is the softmax of Zj, right? Again, we know how this works. And so Aj is e to the power of Zj by j equal to 1 to k e to the power of Zj. So what we get is minus AI Aj. So if it's AI, derivative of AI with respect to Zj, the output is minus AI Aj, right? So for this derivative now, if I is equal to j, the derivative is AI, right? With brackets 1 minus AI. And if I is not equal to j, it's minus AI Aj. Simple, right? Okay, so now that we've got this derivative of the softmax, let's look at an example. Take this input. We've got the output of the softmax. We know how this works. So first term here, it's a 3 by 3 because we're looking at a 3 by 3 example, is A1, 1 minus A1, which is 0.18 times 1 minus 0.18, which is 0.1516. The second term here, right, which is dou A1, dou Z2, right, is minus of 0.18 times 0.31, which we have here. What about the second term here? You can fill in the rest. Try it out. It'll be interesting. So you have A2 times 1 minus A2. So 0.31 times 1 minus 0.31, which is this term. What about if it's, this term, right? Derivative of A2 with respect to Z3. So it's minus 0.31 times 0.51, which is this. So I filled in the rest. Hopefully, you've tried this out and you've got the answer as well. If not, just go back to the previous page, do this by hand, and it'll be an interesting practice for you. But now we see how we can get the derivative of the outputs of the softmax with respect to the inputs. And we're not done, right? This was the way the backward sensitivities are. We've got this that has been passed back from the loss function. We're not worrying about the loss function now. We'll do it in the next video where we look at the NN cross entropy loss, which is what is used with the softmax. But for now, we're just assuming we've got the derivatives of the loss with respect to the outputs of the softmax. We've just computed the sensitivities of the softmax, right? We've got that matrix, the derivatives of the outputs of the softmax with respect to the inputs. We now need to change this to get what is passed back from the softmax function. So the derivative of loss with respect to the input is basically the sum over j, the derivative of the loss with respect to aj times the derivative of aj with respect to zi. They're all partials, right? With respect to zi. So the dual to zi is this, right? So for example, dual to z1, for example, and in this case, I'm just assuming there are many, but I'm showing you three terms because that's the example we're going to use, is the derivative of the partial of L with respect to A1 times, so the dependence of L, on A1 times how, A1, partial of A1 with respect to Z1 plus the partial of L with respect to A2 times the partial of A2 with respect to Z1 and so on. So here it's always Z1. The end of this, you get this for how many other terms you have, and you get the derivative of L with respect to Z1, right? The dependence through A1, through A2, through A3, and so on are all covered. We can now write this in matrix form. What we can do is say, well, do L, do Z1, do L, do Z2, and so on. We can write that as a column vector. We can take the sensitivity matrix, so the Jacobian matrix as it's called, of the softmax, but now we're going to flip it. We're going to take the transpose of it, right? We're going to write that here, and then we're going to write the value, the matrix that's, or the column vector of sensitivities of the output of the softmax that's passed back from the loss function. So what do we get? Well, we get dou L dou Z1 is dot product of this row of the matrix with respect to this column. So it's dou L, technically dou A dou Z1 times dou L dou A1. Let's read it the other way. Dou L dou A1 times dou L dou Z, dou L dou A1 times dou A dou Z1 plus dou L dou A2 times dou A2 dou Z1, and so on all the way to dou L dou AN times dou AN dou Z1, which covers the sensitivity of loss passed through A1 all the way to AN with respect to Z1. You do the same with respect to Z2, Z3, and so on all the way down to Zn. And so that allows us to use matrix operations to get this, right? So for a three-dimensional example, the 3 by 3 case we looked at, same thing, but now I've reduced it into a 3 by 3 matrix and same operation, right? So let's do an example. Now, if you remember how these are computed, we've computed this. If you note, and I forgot to mention it there, you see that this matrix actually shows up to be symmetric, right? You have the diagonal terms, which are unique, but then the off-diagonal terms, because it's minus AI AJ, and here it would be minus AJ AI, right? So when we compute it this way, we see that for simple examples, if you compute the matrices exactly, you end up with a symmetric Jacobian. And now to get dou L dou Z1, it's basically this dot this, which is this value. Dou L dou Z2 is the second row dot this column, which is this. And the third is this dot this, which is this. And so we've fairly quickly, using this matrix operation, computed the sensitivities of the loss with respect to the inputs of the softmax, which can then be passed back to the hidden layers of the neural network in our case, right? This was, just to repeat, this has been passed in from the loss function, and this is the transpose of the Jacobian matrix we have computed, right, in the previous few slides, which we've seen in our case is symmetric, right? Okay. So that gives us an understanding of how the backward pass works for the softmax as well. We've seen the forward pass, which is very simple, but we've seen how the backward pass works as well, where the loss passes the values back, and then the softmax takes that, and then you get the sensitivities of the loss with respect to the inputs to the softmax, which is then passed back through the neural network. In our case, it would be tanh layers, right, which we've seen in the previous video. So let's quickly go and implement just the softmax. Now, just a note, when we get to the loss function, the NN cross entropy, combining that with the softmax, we'll have a more interesting, fairly simpler implementation of this. So we'll then fix it or correct it or update it, depending on how you want to think about it when we get to that video. Let's now implement the softmax function / layer. So it's the same notebook that we've previously implemented the layer and the neuron, and that was basically a tanh layer, so the linear part plus the tanh activation function. We're now going to implement the softmax. So we're going to say class softmax, call it a class. Now the softmax has, as we know, no parameters, so we're going to say just initialize it, and I'm going to say softmax, it's not cross entropy, and it's basically got, I'm passing in the number of inputs, and I'm saying the output, which we're going to call A, is basically of size number of inputs, right? Because number of outputs in the softmax is equal to the number of inputs. Let's now write the forward pass. So the forward pass is exceptionally simple. Typically all forward passes are, right, for neural networks and neurons. You pass in the x, which is the input vector, saying numerator is np dot x, so it's going to take the exponential of each of these x terms, and then the denominator is basically np dot sum the numerator, right? So it's just going to sum each of these numerator terms, and then the value a is basically the numerator, which is the numpy exponential divided by the denominator. So this is the sum term, and this is the exponential in the numerator, right? And that's it. That's the forward pass. Okay, now the backward pass, what we're going to do, I'm going to make this slightly interesting. I'm going to first put a scalar implementation. So say the backward, you've passed in the derivative of the loss with respect to the outputs. Let's say you have a dA dz, which is a Jacobian matrix, which is what we want to compute, is np.0 self.inputs, right? The dimension is because the number of outputs is equal to the number of inputs. So what is the actual implementation we're going to be doing? We're saying, well, for each row and column, for the diagonal terms, so I is j, the derivative term is a times 1 minus a, right? And for the off diagonal terms, it's minus ai, right? Minus ai times aj. And so that's what this does. It loops over the number of, it loops over a, basically it's n inputs, and then if I is j, meaning the diagonal terms, you get a times 1 minus a, ai times 1 minus ai, and if not, you get self.ai aj. Now this is a scalar implementation, and even, right, however, we can speed this up with a slightly more interesting vectorized implementation. Even though we have not vectorized our tanh neuron layer, it's an assembly of tanh neurons, but the neurons are vectorized. In this case, the softmax is, you can think of it as a function, a neuron, or a layer. And so the better way to write it is dA dz is np.outer self.a self.a. What it does is basically compute, and there's a minus here, ai aj, right? The outer product will basically take a1 times a1, a1 times a2, a1 times a3, and so on. So the outer product does that, and then np.fill diagonal will take each of the diagonal terms of dA dz, and in the diagonal terms it will replace them with self.a times 1 minus self.a. So the diagonal term will get replaced by this. So that's a fairly more, cleaner implementation. And then we want to do the chain rule. So chain rule, right? And so the chain rule is basically a dot product, right? You want to take a dot product of this, right? Only thing is now here you want to transpose it. So you're going to say dot t, which will transpose dA dz. Now because it's symmetric, you technically don't need to do this, but I'm going to keep this like this because it's the accurate implementation, right? So you take the the transpose of dA dz, and then you use a dot product to get the dot product with respect to the loss vector passed in. So we are going to store the derivatives just so that we have a reference point, and so we're going to say that, and that's it. That's the backward pass. So let's see if this works. Now what we're going to do is we are going to make sure we visualize this. Let me just write the softmax. So the softmax layer we're going to create is 3 inputs. We're going to use the inputs in the exercise so that we can make sure we're getting it right. So the inputs are basically which is the x, right? The x here is basically this, right, which is what we used in the example. Let me just actually just go back up, run this, and then we come back here, and so the softmax is fine. I'm saying x is this, and so it's saying softmax layer is not defined because I've called it softmax, not softmax layer. That's my bad. Okay, so we're good. And now the forward pass, so a is softmax on forward, right? And we get the values, and this is pretty much what we got, or what we have shown you in the slides, so that's correct. Now the backward, we're using the same values as we did in the slides, so that's dLdA, and then what do? You say dLdz is softmax dot backwards dLdA, and we'll run that, and you get the same values we see in the slides, right? Now I'll encourage you to go and check this out, but this is it, right? So it's a fairly simple implementation. We've got the forward pass, which is just the the exponential by the sum of the exponentials, and then the backward, right, which we've used simple matrix operations to compute that. Okay, back to the slides for a second. In the next video, we're going to be covering the NN cross entropy loss, right? Which is a loss function we're going to be using to calculate the loss and train the neural network for classification. So see you in the next one.